Let's try an example for these indeterminate products. So in this example, we're going to do the limit of square root x times natural log x, so it is a product, and we're doing the limit as x goes to 0 from the right. All right, so x is approaching 0, but we can't actually plug 0 in to the log function, so we kind of have to handle each of these separate pieces. Just think about what each of those individual limits are. So we might try, as a first step, we want to see what form we have. So we're going to try the product limit law first, just to kind of see what's going on. So we have a product here of two functions of x. Let's split this limit up. Let's look at the limit of just the square root term as x approaches 0 from the right, and times the limit of just that natural log function as x approaches 0 from the right. Now that square root function, we can actually do this. We can plug 0 in, and we get 0. So that's not the issue. It was this natural log function. We can't plug 0 into that. So it comes down to just knowing, well, what is the limit of our natural log function as x approaches 0 from the right? Well, that's minus infinity. The log function gets really large negative. So this is a 0 times infinity form. Indeterminate product. All right, so we're kind of stuck. And our idea that we kind of outlined, our strategy, is to rewrite this function as, instead of a product, try to write it as a fraction. So that's what we're going to do. We're going to rewrite this as a fraction. All right, so we have some options here. There's two pieces of our function. There's the square root, and then there's this natural log. And what we saw before in our strategy is we have to pick one of these pieces here to put in the numerator, and then the other one we do the reciprocal and put it in the denominator. All right, so we need to decide which one, and just pick one. See where you go. So let's pick. What should we pick? Well, let's pick the natural log. We're going to pick that to go in the numerator here. And so the one that we don't pick, we do its reciprocal and we put that into the denominator. So we're putting 1 over square root x in the denominator. All right. So we've written this as a quotient. We've written it as a fraction. Why is this helpful? Well, let's check now to see what form we have. All right, so x is approaching 0 from the right. What happens to this natural log function? Well, we said that goes to minus infinity. What about this 1 over square root x term? Well, this is a c over 0 form, and you can check that it goes to positive infinity. So this is a c over 0 form. We know that's at infinite. You can use a test number here. Plug a slightly positive number in, so 0.1. Everything's positive. We go to positive infinity. So we have this c over 0 form here for that 1 over square root x term. And so what we end up with is this whole big fraction now, these fractions stacked on top of fractions, is an indeterminate quotient, and this is the correct form. So we can't go any further with this in terms of actually answering the question, but we can use L'Hopital's rule now to convert this limit into a brand new limit. And that's what we're going to do next. So we're going to apply the rule. We have a quotient now. It's of the right format. It's of the right indeterminate form. So we're going to apply the rule, put a little h there to denote what we're doing. And we're going to differentiate the top, differentiate the bottom. And we know we're going to differentiate this 1 over square root x. So let's write that instead of a root sign, let's write it as a power function. And instead of a fraction, let's use a negative exponent. So we're going to write that as x raised to the negative 1/2. We know that's how we generally differentiate those things. And we're going to apply the derivative to the top term and the derivative to the bottom term. That's what L'Hopital's rule says. So we're converting this into a brand new limit now. Let's calculate these derivatives. So the derivative of natural log is 1 over x. And derivative of this x to the negative 1/2 is negative 1/2 x to the negative 3/2. And we have this brand new limit now, and we should try to simplify it if possible. And we can actually simplify this one. So what might we do? Well, I want to get rid of this x, so let's multiply the top by, or this, I want to get rid of this 1 over x, so let's multiply the top of this fraction by x. And if I multiply by x, then I have to do that down here as well. So if we do that, and you know what, while we're at it, I want to get rid of this 1/2. So let's multiply, or let's get rid of the negative 1/2. Let's, while we're at it, multiply by negative 2. So I want to get rid of the negative 1/2 down here, so I'm going to multiply by negative 2, and then I have to do that in the numerator. All right, so let's see what we get. We're going to have the limit, and doing this, we're going to end up with negative 2 over, the x's here cancel, and then the negative 2 and the negative 1/2 cancel, and then I have this x right here, and this x raised to the negative 3/2. I multiply those together and I add the exponents. So there's like a hidden 1 right there for our exponent, and when I add those together, I get x raised to the negative 1/2. And now this is, I have a negative exponent, so I can keep rewriting that. So instead of having a negative exponent, I could get rid of the fraction completely. So this would be negative 2 times x raised to the positive 1/2. It's almost like I'm doing a double negative, and it ends up becoming a positive exponent when I get rid of that fraction. So I continue simplifying it here. And now I'm at a point where I can just plug in. I can plug into the square root function, and I get 0. And that's my limit. Limit here is 0. What did we do here? Well, we just did direct evaluation. Continuous function. Square root's continuous at 0. All right. Not too bad. It took a little bit of work, but we were able to get some L'Hopital's rule in here. And we had to do a little bit of algebra to simplify our limit down, but we got it. And it all came down to this key step of, we first identified that we had an indeterminate product, and then we rewrote it kind of cleverly as a fraction. So we decided, all right, let's take this natural log function. I'm going to put that on top. And then I take this other piece, this square root x, and I kind of do the reciprocal and put that in the denominator. So 1 over square root x down there. And it turned out it worked. Now the question is, what if we chose differently? Why did I pick natural log up here? Why did I put that up there? I tried it out. Tried it out ahead of time. Maybe you pick wrong. So let's see what happens. Let's try it again. And let's try instead, let's pick this square root term to go on top of our fraction. Let's see what happens. So we're going to do the limit as x approaches 0 from the right. We're going to throw our square root term up there. And then in the denominator, I'm going to do 1 over natural log x. Seems reasonable. And this is of the right form. So the top term here is going to 0. The bottom term here is a c over infinity form, so that goes to 0. So this is a 0 over 0 form, which is good. So we could use L'Hopital's rule. So we're going to differentiate the term in the top. And we know we're going to differentiate this 1 over natural log x. So let's actually write that as natural log x raised to the negative 1, just to help us with the differentiation. And actually, instead of square root x, let's write that as x raised to the 1/2 while we're at it. We're going to apply the derivative to both the top and the bottom. That's what L'Hopital's rules tells us we can do because we have this correct form. And we differentiate, so derivative of x to the 1/2, we just use some power rule there. We get 1/2 x to the negative 1/2. And then differentiating this natural log x raised to the negative 1, we use chain rule. So we bring down the negative 1. We keep what's inside the parentheses the same. We subtract 1 from the exponent, so we're down to negative 2. Then we take our inner function and we multiply by its derivative. And oh boy, this is looking complicated. More so than what we had before. So before, we ended up with 1 over x times x, 1 over x and then x to the negative 3/2 in the denominator. Both of those were just power functions. And that's okay. We were able to do some algebra and simplify them down. Here, we still have this, we've gone through this, clever trick, and this is all fine what we've done so far, but we still have that natural log function. We weren't able to quite get rid of it. So at this point, maybe there's a little algebra we could do, but if you get to this point and it just feels like you've made things more complicated, go back and try the other way. So not necessarily wrong. Maybe there's a clever way to rewrite all this. But if you get to the point where it looks like you're just getting more complicated and it looks like it's not going to simplify down, notice we started with a natural log x. Now we have this natural log x squared term. So it's kind of raised the power in some way on the natural log term. So it's made it more complicated. So if it looks more complicated, try the other fraction. And we saw that one did work. All right, so that's our strategy here for these indeterminate products. And this was a good one to try. But you have options, when you try rewriting these fractions. Sometimes both of them work. Sometimes one of them is only going to work. And you just got to, try one and see what happens. And if it gets more complicated, then try the other one. All right. We'll look at some more indeterminate forms coming up.